Okay, what this is, it's a kind of a quick summary, but with a historical context. Observational cosmology started in the 1920s through the optical observations of galaxies. Edwin Hubble took the crucial step of establishing the distances of galaxies, showing that faint little nebulae, little blobs of fuzz that were seen in photographic plates at that time were galactic systems equivalent to our own Milky Way. He showed the vast size of the universe, the linear relation between redshift and distance, and he used number counts to establish the rough homogeneity of the universe. So he laid the foundations of cosmology as a quantitative subject. Now, just to sort of put the context, this is a fraction of the Milky Way, our own galaxy with 100,000 million stars. That's a typical star cluster in the Milky Way. The Andromeda galaxy is our companion, and we believe it's about the same size as our galaxy and the same sort of shape. And if we were in Andromeda, we would be somewhere way out towards the rim there. These are satellite galaxies, and of course all of these stars in the front are stars in our galaxy which are intervening before you see the Andromeda galaxy. The scale is about 50,000 light years, 30,000 light years across, and about 1 million light years away from us. About 100,000 million stars, and then of course the big thing about galaxies is we see more and more galaxies as we look further out. We see barred galaxies, we see ellipticals, we see spirals, we see interacting spirals, and we see them in clusters, and the further out we look, the more clusters we see of galaxies. And in fact, in the visible part of the universe, we see about 10 to the 11th galaxies, 100,000 million galaxies. Now, this is Hubble's very famous diagram from 1929, showing the spectra of galaxies. You see a picture of the galaxies, and from its apparent size, you estimate its distance, and the distance estimations are down there. So the further ones, of course, looking smaller. This is the angular diameter test we're using here. And then the redshift, you see these K and H lines shifted in the spectra of the galaxies because they're moving away from us. These are lines of calcium in those galaxies, and you have the deduced speed under there. And so you get the very famous diagram, Hubble's diagram from 1929, of distance this way and redshift this way, written as velocities. Now, people later on have looked at these curves and said actually a quadratic curve would fit that at least as well as a linear curve, and that is probably true. Nevertheless, in fact, Hubble was exceedingly lucky in many ways to get this graph, because given what we know now about large-scale structure, he was pretty lucky to get a patch which, in fact, on those scales showed the expansion of the universe. Now, the theoreticians came in, and in 1917, Einstein came up with his first static universe model. De Sitter immediately found his universe model. And these were replaced after some resistance by the expanding universes of Friedmann and Lemaitre, 1922, 1924, 1927. They produced them, but they were not accepted until about 1931, which was the time at which it first began to be accepted that the universe was expanding. And we then get the standard models of the universe, which are exact solutions of the Einstein field equations. They have a Robertson-Walker geometry, which is that they are spatially homogeneous and isotropic. Everything is the same at the same time, no variation, with spatial place, and isotropic meaning whatever direction you look in the sky, you see the same thing if you are looking on a large enough scale. That means these geometries can characterize by a scale factor, commonly called the size of the universe. That's a rather misleading kind of title, but what it means is everything scales with the scale factor on large scales. It gives you then the Hubble rate, which is 1 over the scale factor times the rate of change, which is the Hubble parameter and changes with time. And from this we get the basic observational parameters, the Hubble constant, which is the Hubble parameter evaluated today, the matter density for all sorts of different components. And one of the really important issues for cosmology is what those components are. Then there's the deceleration parameter, the inverse of the Hubble constant squared, 1 over the scale factor, the second derivative squared of the present time. And this is telling you how fast the acceleration of the universe is speeding up or slowing down. It has a minus sign, so it is positive if the universe is slowing down, which is what everybody has expected would be the case. In these models, there can be a cosmological constant, which is a repulsive force proportional to distance. and they have spatial curvature, which can be +1 if they're spherical, -1 if they're hyperbolic, and is 0 if they are flat. Now, from these, we form the normalized density parameter. We take the total density of matter, multiply by the gravitational constant, and divide by 3 times the square of the Hubble constant, because this gives you a critical a dimensionless quantity whose critical value is 1. And what does that critical value mean? Well, what it means is it's the difference between models which recollapse and models which expand forever. You're at the critical density. If you have no cosmological constant, you are precisely at omega is 1. In this case, omega is bigger than 1 in the models that recollapse, and omega is less than 1 in the models that expand forever. Now, these come out of the basic equations for cosmology, and the basic equations are the energy conservation equation, the Friedmann equation, which is the dynamical equation, and from these you get these basic behaviors. For normal matter, there's always a singular start. If k is +1, it recollapses. K is -1, it expands forever. And k is 0, the critical case, it just expands forever. Now, that's the behavior when the cosmological constant vanishes. When it's not 0 and k is +1, the universe can bounce or it can hover close to a constant radius. It even allows a static solution. So what one must remember in cosmology, all the interesting dynamical behaviors occur for k is +1, for positively curved spatial sections. The other cases, basically, they just start off and then they expand, and so they are relatively uninteresting. Where do you get these results from? From this equation here, because when you want a turnaround, you have to put the Hubble constant equal to 0. At that turnaround point, the energy density is positive. The cosmological constant will be positive under most ordinary circumstances. And so if you're going to get a turnaround point, you must have k positive. That immediately follows from the Friedmann equation. So we have that basic behavior. And from this, we can then work out observational relations, the numbers of galaxies with their magnitudes, the magnitudes with redshift, and you can apply these to standard candles. Now, Hubble tried number counts as a function of magnitude, and he showed the universe was approximately homogeneous, but he also established that the number counts were so inaccurate you cannot use them to determine the spatial curvature. What he had hoped was he would find the spatial curvature, and you can't do that from number counts. Alan Sandage and various other people had a huge program through the 1960s trying to determine the deceleration parameter, and hence the amount of matter in the universe, from the magnitude redshift relation. That is, looking at the brightness of distant galaxies as a function of redshift. And in fact, that Hubble diagram we just saw was the first magnitude redshift diagram which was reliably obtained. The problem is you've got to apply it to standard candles, and standard candles are galaxies or quasi-stellar objects or radio sources or something which has got absolutely standard properties. The trouble is there are no good standard candles, or until very recently there were no good standard candles. So this huge program running through the 60s, 70s to the 80s failed. It failed to determine the spatial curvature of the universe, and it failed to determine the deceleration or acceleration of the universe, partly because of source evolution. As you look back into the past, you're seeing sources as they were a long time ago, and they did not then necessarily have the same properties they have now. There was a huge debate about that in the 1960s, and the one thing that was established is that sources do have serious evolution, which means you cannot use the magnitude redshift diagram to determine the deceleration parameter for galaxies, quasi-stellar objects, radio sources, and similar sources. And the other thing is there's a huge amount of simply statistical variation. Galaxies come in all sorts of sizes and brightnesses, and so do radio sources, quasi-stellar objects. So this prevented determining the deceleration parameter. What did happen, though, was we did establish that there was a very linear velocity-distance relationship out to much, much further than Hubble. Hubble determined the little block at the far left, and it was extended to a huge amount further. That's a schematic diagram, obviously. Now, astrophysical cosmology came into play, studying the properties and evolution of galaxies, clusters of galaxies, the intergalactic medium, radio sources, quasi-stellar object, X-ray sources, an immensely rich series of interactions taking place between the medium, the radiation, and all of these different kinds of sources. And the one absolutely definite thing that came out of this was the discovery in the mid-1960s that these sources evolved with time. In particular, radio source counts are inconsistent with a steady-state universe. It was proposed in those days, in the early 1960s, that the universe could have been in a steady state, that there could have been a Hubble constant which was invariant with time and a density parameter invariant with time. Now, you can't get that with the Einstein equations, so you have to say general relativity has to be modified a little to make that happen. And Bondi, Gold, and Hoyle were punting this theory at that time, and it got destroyed by the radio source counts, which are incompatible with steady-state universe. Actually, it's much worse than that. The radio source counts are incompatible with all Robertson-Walker models unless there is serious evolution of either the numbers or the luminosities of the radio sources. Astrophysical cosmology goes on to ask us, what is the origin of structure in various scales? What's the origin of rotation? What's the origin of magnetic fields? All of these things one wants to know, what is their origin in astrophysical cosmology? Looks at that. The key discovery that came out of all of this is that the rotation curves of galaxies and the motions of galaxies and clusters indicate the presence of dark matter. If you take the velocities of rotation of a galaxy and model it in terms of the matter present that you can see, the luminous matter, there isn't enough to give you the rotation curves that you see. Similarly, clusters of galaxies, there isn't enough matter that is visible in order to give the velocities which are seen. And so there has to be, holding them together, dark matter which is unseen. It doesn't radiate, but is felt through its gravitational field. And in terms of the density of dark matter, it varies with scale, but at the cosmological scale contributes about omega is 0.3 in terms of that density parameter. Now, there's an important point about this, which is this is much less than the critical density. So it's much less than the critical density, but it is much greater than the amount of matter we see. So there's a large amount of dark matter. Following the universe back in time, it heats up, and hence there was a hot Big Bang era in the very early universe. In these very hot early times, there's equilibrium between matter and radiation, and hence you get blackbody radiation coming out of this early epoch because matter and radiation in equilibrium give you blackbody. And this radiation was emitted at about 4,000 degrees K, but the universe has expanded for a factor of about 1,200 since then, and it has cooled to about 3 degrees Kelvin, or more accurately 2.75 degrees Kelvin. That means it's exceedingly difficult to detect, and if you want to get good measurements, you need to get above the atmosphere, which is why we couldn't do this accurately before the Second World War. And you need to measure it very accurately at the 1 millimeter peak. And it was discovered in 1965, giving the Nobel Prizes to Penzias and Wilson, even though they discovered it more or less by accident. Now, the existence of this radiation is incredibly important because it vindicates the application of standard physics to the early universe. Indeed, because it's blackbody radiation, it tells you quantum physics applies unchanged in those very early times, because that's where the blackbody spectrum comes from. And this radiation reaches us from the surface of last scattering at about 4,000 degrees. At earlier times, the matter in the universe was ionized. It was atoms and electrons mixing through each other. The radiation scattered off the electrons, and so the early universe was very, very opaque. As you go through 4,000 degrees through the ionization temperature, the matter combines to form atoms, and as soon as that happens, the universe becomes incredibly transparent. Now, the big thing we can do with the microwave background is look for its isotropy, and at 1 part in 100, it is completely isotropic, which is a truly remarkable thing. At that level of approximation, the temperature is exactly the same over the entire sky. Its spectrum is incredibly accurately a black body temperature curve, and that shows that this is evidence that the early universe was in equilibrium and that quantum theory was true in the very early universe in an unchanged form. And we get the microwave background radiation coming to us from the surface of last scattering, so this in a sense is an incredibly short kind of picture of the early universe, the start of the universe over there, a very, very rapid expansion, which I will talk about. At the early times, electrons, protons, and photons and neutrons in interaction with each other, then the formation of helium through the process of nucleosynthesis, the decoupling of the universe. Matter and radiation are now separated from each other. That means that matter can now collapse to form the initial stages of stars and galaxies, which form, and then we end up here today. And here today, if you look at your television screen, about 1% of the snow on your television screen is due to the photons of the cosmic background radiation, the universe saying hello to you on your television screen. At 1 part in 1,000, you get a dipole. It's as hotter in one part of the sky and cooler in the other side. And at first you might say to yourself, wow, what this means is there's a huge difference. The universe is different that way from that way. This is, of course, an all-sky picture showing this dipole. But the interpretation we put on this is not that the universe is different that way than the other way, but rather that this is because we are moving relative to the universe at 300 kilometers a second, which will cause a dipole in blackbody radiation. So subtract that out, and what you get left with is an isotropy at 1 part in 10 to the 5th. So we are moving relative to the universe. Take it out, and this is what you get left with. Now, this is our own galaxy, and part of the problem in looking at the microwave background is that our own galaxy obscures quite a bit of the sky. And so you have to adopt all sorts of procedures to try to estimate or deduce what is behind our own galaxy. And there are various ways of doing that, and that's a kind of a estimation of what there would be there if our galaxy wasn't in the way. And in principle, what you are seeing is the surface of last scattering, the furthest that we can see by electromagnetic radiation. And you're seeing high density and low density regions. The high density regions will become, later on, clusters of galaxies, and the low density regions will become vast voids in intergalactic space. So in principle, you're seeing the universe as it was, incredibly smooth to 1 part in 100,000 at the time of decoupling, but then gravitational instability sets in and creates structure from this. And you get this very quick sort of thermal history of the universe. This is time across the bottom, or expansion across the bottom, and this is temperature vertically. And at the Planck time, quantum gravity is true. The grand unified time, grand unification, comes to an end. Electroweak symmetry breaking occurs here. Neutrinos decouple here. Nucleosynthesis here. Matter and energy radiation equality here. Decoupling there. And the present day here. The very brief thermal history of the universe, with all of these immensely interesting physical things taking place. For instance, at this point, quarks combining to form protons and neutrons. Because the temperature is going back without limit, as you go back towards the Big Bang, any physical process you can think of will take place as you go back. All of physics comes into play. And this is a little picture, again, of this whole thing. The Big Bang way back there. Inflation, which I'll talk about briefly in a minute. The formation of deuterium and helium. The cosmic background spectrum fixed. Matter and radiation energy equality. Last scattering. Radiation coming towards us. Galaxies forming in the present day. And the analog that is used here is that you can only see a certain distance when there are clouds. You can't see behind. This last scattering surface prevents us from seeing directly any of the things which took place earlier. Now, the origin of the elements, nuclear physics processes took place during this era in the unbounded temperature, implying matter radiation equilibrium, so that the previous state was irrelevant. And as we come through 10 to the 8th, 10 to the 9th, to 10 to the 8th degrees K, there's an epoch of nucleosynthesis when light elements form in the early universe at about this temperature of 10 to the 9th. Neutrons and protons combining to form light nuclei. The heavy elements cannot be created then. They must form much later in stars. So this is the famous diagram. You get out your calculators. You have to do some heavy calculations using known nuclear reaction rates. And what the variable across the bottom is basically the density of ordinary matter relative to the number of photons, because we know how many photons there were to high accuracy because it comes from the microwave background radiation, which is the dominant radiation in the universe. So the number of photons is very, very well known. But the amount of matter is not. It's not known to within a factor, or it wasn't known to within a factor 100, because dark matter is not difficult, is not easy to detect. Now, what happens here, these are theoretical curves for the element abundance fractions of helium-4, deuterium-2, helium-3, and lithium. as a function of the baryon to photon ratio, and a truly remarkable thing happens. What you find is the observed amount is shown by the circles. That's the amount of helium, that circle there, deuterium, helium-3, and lithium. And if you slide backwards and forward, there is just one place where the observations fit with the theory. And that tells you the amount of matter in the universe in terms of the radiations. And it is really, you see, it's not a trivial kind of thing because you're getting 4 different lots of quantities predicted from one variable. So the one variable fix is sufficient to give you the 4 different amounts, all of which agree with observation, and a huge success. And so what you get is nuclear synthesis theory and element abundance observations agree, provided the baryon density is low, about 0.01. You might take it up to 0.02, but a very low amount. The key point is this is much, much less than the amount of matter which we have said exists, the dark matter. This is the amount of baryons which comes from nuclear synthesis. The dark matter estimates from the Astrophysical Cosmology, the difference shows that most of the matter in the universe, 95% of the matter in the universe or more, is non-baryonic. It's not the kind of matter out of which we are made or out of which anything in the solar system is made. So we are unrepresentative of the universe. We're made out of something different from what most of the universe is made out. One of the successes of this theory, and it really is a big success, at the time all of this took place in the 1960s to 1970s, nobody knew how many neutrino species there were. It was known that there were up to 3, but there could have been more, 6, 9 or something. And you can show that this theory only works if there are no more than 3 neutrino species. This was first determined, I believe, from the theory of nuclear synthesis and later confirmed by experiments at CERN. And I think that's a really great achievement of all the people who worked on this hot Big Bang theory, that they predicted that this theory could only work if there were at most 3 neutrino species, as later confirmed by the particle accelerators. Now, if we go back to even earlier times from the nuclear synthesis time, that's when nuclear physics is important. At earlier times, particle physics is important. And the discovery of Alan Guth in the 1980s was that quantum field theory allows a violation of the standard energy density condition. The condition for the universe to decelerate is that the energy density plus 3 times the pressure must be positive. Now, quantum field theory allows you for matter, well, for fields, scalar fields in particular, in which the pressure becomes negative so that rho plus 3p becomes negative. And that suddenly allows the universe to accelerate rather than slowing down. That means there can be a period of very accelerated expansion, incredibly fast expansion for a very short time, driven by scalar fields in the very early universe, and that's what's called inflation. The expansion accelerating incredibly rapidly, taking place through many e-foldings before a subsequent hot Big Bang era begins, when the inflationary field has decayed away and become ordinary matter and radiation. So you get this kind of picture. This is typical of what you've got. The time here, the Planck time, inflation, annihilation of matter and antimatter. Quarks form from hadrons. There's electrons and neutrinos here. 3 minutes when nuclear synthesis takes. There's protons and neutrons form atomic nuclei. The universe becomes transparent, and here stable atoms form, radiation and matter separate, and then you get stars and galaxies. And the forces were all unified, it's supposed, on that picture at very early time, and then gravity separated out, electroweak separated out, and then electromagnetic and weak separated out as the temperatures drop. So this is the kind of potted picture of the physics that takes place in the very early universe. This is a very nice picture showing this again, the radius of the physical universe. This way, the Big Bang, the quantum era, which we don't know much about. I'll talk about that in just a minute. This very rapid inflation, every period up to 10 to the minus 32 seconds, an incredibly small time here, but that is in how fast that is supposed to have taken place. The quark soup going through first galaxies here, and the present day, and it's very important, the total age of this, about 12 to 15 billion years, which comes from estimates of the Hubble constant. Now, the power of the concept of inflation was demonstrated in 1980 by Alan Guth. In principle, it explains the smoothness of the universe and its flatness and the horizon problems. I'm not going to go into those because Roy Martins is going to talk about them later, but basically one of the puzzles in cosmology is why the universe on the large scale should be so incredibly smooth and so flat. The density parameter omega is very, very close to 1. It's almost certainly not exactly 1, but it's very close to 1. That's one thing one wants to explain. The smoothness of these models one wants to explain. And the causality. If you examine causality in the universe, you will find that in an ordinary model, the isotropy of the microwave background is very difficult to explain because the points on the surface of last scattering in that direction were not in causal interaction with the points in that direction. And so it's a big puzzle when you don't have inflation why conditions were the same in these two places. With inflation, they are causally connected, and that in principle explains how the universe could be so smooth and isotropic. Now, the unexpected thing that came out of inflation was it was discovered. The structure formation theories based on inflation predict a scale-free power spectrum for the matter distribution in the universe and a series of peaks in the power spectrum of the cosmic background radiation and isotropies. And this is a real triumph for inflation, the prediction of these peaks in the power spectrum, which then have been discovered over the last 10 years to actually be there. These structure formation theories are based on the idea that in the very, very early universe, you're very, very smooth, but there are quantum fluctuations, and those get expanded up to astronomical scales by the inflationary expansion and become the seeds for the formation of clusters of galaxies. A version of inflation is chaotic inflation, which predicts that not only our universe should be so large and smooth as it is, as we see around us, but that surrounding that, there will be other pockets of expanding universe domains, just like our one, but possibly with different Hubble constants, different matter densities, maybe different gravitational constants, maybe different electromagnetic constants. That we would be surrounded, our pocket of expanding universe, if we went far enough, we would find different pockets with different properties, and between them, the universe might still be inflating even today. The whole thing forming a fractal-like structure, and that's one theory of the way the universe looks in the very large. Now, while all of this physical growth was taking place, there was also a great growing understanding of generic geometrical and dynamic behavior of families of cosmological models. A lot of equations were determined, theorems were proved, phase-plane diagrams found, attractors found, and so on. We obtained a much greater dynamical understanding of cosmology than we had had before from the viewpoint of the geometry of general relativity. And in particular, specific families, the Bianchi models and Tolman-Bondi models were examined in great detail, and I was one of the people who've had a lot of fun looking at these Bianchi and isotropic models and how they evolve and determining their phase planes. Also, important theorems were determined relating the causal properties of these spaces to the existence of geodesics and space-like surfaces, discussing causal violations, and particularly theorems proving the existence of singularities under various plausible circumstances, the famous Hawking-Penrose theorems based on closed-trapped surfaces and geodesic incompleteness. Now, the point here is the following. The standard Robertson-Walker models are incredibly smooth and isotropic. They're perfectly smooth and isotropic, so they're good models on a large scale, but they're not accurate on small scales. And the question was whether the singularity, the start of the universe predicted by the Robertson-Walker models, was a genuine physical feature, or was it there only because we were using oversimplified models? What Hawking and Penrose showed was that realistic models, as realistic as you like geometrically, would have initial singularities, provided certain energy conditions were satisfied, and provided causality was okay. And so they proved really important singularity theorems. Why are they important? Because they say, according to standard classical relativity, the universe must have had a beginning. It couldn't have lived forever. But those relied on the energy conditions. And as we've seen, under inflation, those energy conditions can be violated. So this was in the 1960s and early 1970s. By the 1990s, we had discovered that the energy conditions underlying these theorems need not, after all, be true. So nowadays, it is possible to find non-singular universe models which rely on the violation of those energy conditions, together with having closed spatial sections, that is, k is +1. But that's at a much later time. Existence and uniqueness theorems were proved. In a sense, these are the converse of the singularity theorems, and they're really interesting in that sense. And a huge amount of work was done on approximate cosmological solution, that is, perturbed Robertson-Walker models, which show you how structure grows, how the growth of structure takes place. And there's a really important technical issue here, because this is general relativity. You don't have a fixed background space, and what looks like a perturbation of density may actually just be a perturbation of coordinates, and you have to spend a considerable amount of care and time ensuring that what you're looking is physical perturbations and not coordinate perturbations. Okay, now, theorists, being theorists, started thinking earlier and earlier, and started thinking about before the inflationary area, when some kind of quantum gravity effects will dominate the dynamics of the universe and provide the initial conditions for inflation. And there have been many, many attempts to describe this quantum gravity era, including the wave function of the universe, which Hartle and Hawking have looked at, either through the Wheeler-DeWitt equation or path integral methods, something called pre-Big Bang theory based on string duality, something called brane cosmology, that our universe lives on a four-dimensional brane embedded in a five-dimensional space-time, something called the ekpyrotic universe, where such branes collide, and so on and so on. There's a whole variety, a vast zoo, in fact, of completing models. In all cases, the problem is making a solid link to observational tests, because the proposed particle interactions and or extension of classical gravitational theory is not directly testable. You're coming to a domain in the early universe where the physics is completely inaccessible because our accelerators can't get there. The energies are far too high. These theories are indirectly testable via their effects on the inflationary perturbation spectrum, and so on structure formation. And so what we're doing all the time now is making theories trying to link those very, very early times through to structure formation in the cosmic background radiation spectrum, and then testing them by observations. And Roy Martins and Peter Dunsby will talk about this next week. But it's really important to understand there's no fully formulated theory of quantum gravity, so all of these are botch-ups, they're patch-ups, they're partial uses of quantum gravity, they're sort of guesses of what quantum gravity will be like in cosmology, in the face of the fact we don't have a good theory of quantum gravity. So one must treat the whole lot of them with a considerable degree of circumspection. And a final theme that has been coming to the fore in many recent analysis has been the idea that there is an ensemble of cosmologies out there, that ours is not the only universe. And so there's the idea, for instance, it could occur through quantum theory, through what is called the Everett-Wheeler interpretation of quantum theory, where space-time keeps on dividing into more and more universes, or at least that's one way of saying it. You may have read David Deutsch's book about this. There might be a continual production of big bangs in chaotic inflationary theory. And in chaotic inflationary theory, new big bang domains are starting all the time, and they keep on multiplying. And so you could say in some ways that's a multiverse. It could be related to multiple vacuum energy minima, which then condense out in different places in different ways. Or they could be completely unconnected universes, and all of these are being suggested at the present time. You may have seen a Scientific American article on this recently by Max Tegmark. Now, these various proposals then suggest there exists a multiverse, that we aren't in the only universe, that there are all these other universes out there. This potentially brings cosmology within the realm of statistical analysis, giving a basis for using probability theory to look at the nature of the universe. But it denies the uniqueness of the universe. When I started cosmology, there was one universe, and only one universe. And that creates all these special properties of cosmology as a theoretical subject. The idea of this multiverse is to say it's not the only universe, so you can apply statistical techniques. And it therefore provides the only scientific basis for attempts to use the anthropic principle to determine the values of parameters such as the cosmological constant, for which we otherwise have no plausible explanation. Now, the anthropic principle means we look at the universe and say, wow, the universe allows us to exist, it allows intelligent beings to exist. But most universes will not allow life to come into existence. And so you can spend a whole lot of time pondering why it is that our universe allows life to come into existence. And in fact, you can easily see there's a subset of universes which allow life to come into existence. For instance, if the cosmological constant is too large, no structure will form. And that is the end of the possibility of life in the universe. So what you can do here is you can say, well, if we scatter universes around with all sorts of properties, most of them won't allow life to exist because the cosmological constant will be too big, or the lifetime will be too small, or the electromagnetic constant will have the wrong value, and so on and so on. But what you can say is if there are enough universes, if everything happens that can happen, then in some of those universes things will come out right and life will come into existence. And that's the basic way that you try to use the anthropic principle together with an ensemble to explain why life is able to exist. The trouble is the whole of this is completely unverifiable. It is metaphysics rather than physics in my viewpoint, because the supposition of the existence of these other universes cannot be tested by any experimental or observational means. Now, since the 1916s, observational cosmology has gone through a major transformation. The discovery of quasi-stellar objects, X-ray sources, gravitational lenses, and so on, which has been made possible by a revolution in observational technology. New telescopes, ground-based, borne aloft in satellites and balloons, operating at all lengths from radio to gamma ray, and with features such as multiple mirrors and adaptive optics. And we have a marvelous example of that coming up at Sutherland in the SALT telescope. At least as important has been the improved detectors, allowing much better observations and number counts than before. Photomultipliers, CCDs, which have taken over from photomultipliers, interferometers, optical fibers, automated measuring machines, and improved understanding of the selection effects go with all of this. So a huge revolution is taking place. So, for instance, the Hubble Deep Field, the deepest field we have ever got in great detail, a 30-hour exposure time. And the hugely important thing about this is that each of these tiny little dots there is galaxies. As far as we keep looking, even from the Hubble telescope, you keep finding more galaxies. For the first time, we've been able to produce these diagrams of how galaxies are spread out in distance from us. Now, the galactic plane here is blocked out by our galaxy. We are there. But the point is we've had sufficient redshifts to plot galaxies in distance from us, and we see this soap-like structure with the vast walls and the vast voids. The galactic structure on this scale, look at this huge wall over here, is not homogeneous. It's got walls and voids. And this is the soap bubble type structure we see on very large scales. Gravitational lensing, one of the most beautiful things we've discovered, and it's quite difficult to see until you get used to it. Once you start looking at it, you can see circular arcs here, all centered here. You can actually see a circular kind of structure here, all based here, because the gravitational mass there is bending light, and these are very, very distant galaxies that have been lensed. And here is one of the famous pictures here. These are very, very distant galaxies which have been lensed by the central object. Gravitational lenses have been discovered about 1980, and now a huge amount of time and effort has gone into looking for them and deducing from these distorted images how much mass there is there causing the distortion. The first key set of observations that has resulted from this new wave is the study of supernova in distant galaxies provides a usable standard candle for the first time in cosmic history, because the maximum brightness of distant supernova is correlated to their decay rate. Now, we don't know why that is. We don't have a good theory of supernova, but we believe as a matter of observation that the maximum brightness is supernova. It goes to a maximum, it decays away. With the redshifts of the supernova, this gives the first reliable detection of the deceleration parameter Q0 and shows the universe is presently accelerating, one of the most unexpected discoveries of the past decade. We were expecting the universe to be slowing down, but it appears that it is speeding up. Consequently, there's an effective positive cosmological constant with omega lambda about 0.7, 7/10 of the critical density, but tending to make the universe accelerate. And this is what has been called dark energy or quintessence. This is one of the really unexpected things which has been discovered. That's a supernova. Oops, that's the supernova there, which was discovered in that galaxy. That's the rise and fall time. That's the spectrum. You put it all together, and you get this very famous diagram showing redshift and magnitude. It's the old Hubble diagram we started with way back in 1929, but now it is extended, and the first time you see it is slightly bending upwards. And the bending upwards there means that the universe is accelerating, not decelerating. And you plot that, you plot the amount of matter against the cosmological constant. For a few supernovae, you get those confidence curves. For a lot of supernovae, you get these confidence curves here. Your best point is somewhere about there, and it is definitely a positive cosmological constant. And so this is the evidence for the universe accelerating. There are two different supernova teams that have collected data. It's not just one team, which is very important. The second key set of observations is the measurement of the spectrum and anisotropy of the cosmic background radiation by the COBE satellite, Boomerang, Maxima, and later satellites. And the first thing is the extraordinary accuracy of the blackbody spectrum, which I've already commented on, I think. And the second is reliable detection of a quadrupole anisotropy, the angular power spectrum peaks, and the beginnings of the detection of predicted polarization. Now, we've already seen this one. This is the MAP satellite, the 1 in 1,000, where you see the dipole, and you knock the dipole out, and you get this as the dipole at 1 part, the anisotropy at 1 part in 10 to the 5th, much more accurate than the COBE picture we looked at before. And you get the spectrum, incredibly accurate blackbody spectrum, which I've already commented on. And what you get here is the power spectrum. Now, this is wave number. This is large angles over here and small angles over here, and this is the power at each angular scale. And these are theoretical curves for different models, one with no cosmological constant and high density, one with no cosmological constant and low density, and one which corresponds to the Concordance Model today with a 0.3 for the matter and 0.7 for the lambda. And what you get predicted is the Sachs-Wolf plateau at very high angular scales, and then a series of peaks. Now, these peaks come, as will be described for you later on, because the whole universe acts as a huge oscillator on very large scales, with pressure holding it apart, gravity trying to make it collapse, and it oscillates. And this is the size of the largest oscillatory peak at the time of last scattering, because what we're seeing here is what the universe was like at last scattering. And so these are a set of the observations, and that looks a bit messy. That was a while ago. This is a more recent set of observations, and here is the theoretical curve that fits it to a very good approximation. We can debate about the details, but you definitely are getting the first peak. You're getting the further peaks. These peaks were predicted before they were ever seen, and we must say that the inflationary theorists have done an incredible job in predicting that we would see this in the microwave background, and bingo, there they are. And by looking at the position and the height, you get estimates of the Hubble constant and the density of matter in the universe. And so that diagram we had before, we had the supernova over here, and the cosmic background radiation comes in with these confidence curves, and you find there is a domain there in which the microwave background and the supernova agree and give you the best fit or concordance model of the universe, which is the best fit which everybody agrees on today. So the concordance model. Expanding Friedmann-Lemaitre model evolves from a hot Big Bang era when nuclear synthesis took place, and most people believe it was preceded by inflation. The universe has nearly flat space sections as expected on the basis of inflationary theory. The total density is the density of the matter plus the radiation, the lambda 0.3 plus 0.7 is about 1. There's both dark matter and dark energy at late times, a Hubble constant of 66 plus or minus 10, an age of 1.4 plus or minus 2, and that's a little bit small for some globular clusters, but the whole thing does basically fit together and give us a successful concordance model. So we could have had positively curved spaces which will recollapse in the future. We could have had low-density open universes which expand forever without accelerating. What we seem to have is this one, the low-density universe with accelerating expansion at the present time. And the implication is, unless something strange takes place, the universe will not recollapse. It's very, very difficult indeed to get a model where it recollapses because the cosmological constant is pushing it apart. Even if that decays, the amount of matter in the universe is not enough to cause a recollapse. So, there are different views on the nature of cosmology. And the first view is that cosmology is solved. The era of precision cosmology has arrived, and only the details remain to be sorted out. Our main concern is to get ever more accurate values for the various parameters involved. Querying the inflationary standard model or searching for alternatives is a waste of time. quantum cosmology does not have to be solved because its detail get ironed out by inflation. The remaining relevant uncertainties will vanish as we improve our observations, which will enable us to refine the theory as needed. So that's the one view of what we have achieved. Second view, cosmology is a disaster because we don't understand any of its main dynamical features. There's no clarity concerning the quantum gravity era, which sets the stage for all the rest of it. We don't have any clear idea what specific feature underlies inflation. You see, inflation isn't a theory. It's a vast family of theories. There are something like 100 proposals on the table for what the inflaton can be. What that means is it's not actually a serious physical theory linked into any specific physics. It's a potential theory potentially linked into physics, but that link has not actually been made. We don't understand the dominant dynamical features of the present era because we don't know what the dark matter is that's dynamically dominant. We know it's not baryons, but that's basically what we know about it. And we have no idea why there's a small non-zero cosmological constant dominating the largest observable scales. Indeed, quantum field theory gives an answer for the cosmological constant that's wrong by 120 orders of magnitude, which has been characterized as arguably the greatest qualitative discrepancy between theory and observation in the history of science. And there's no clear resolution in sight of the cosmological constant problem. But inflationary theory depends critically on this faulty theory because it's the quantum vacuum idea which underlies inflation. So on that view, cosmology is in a pretty poor state. Yeah, we've got some ideas about what's happening, but actually we don't understand any of its major dynamical features. Well, the third view, the middle way, is a positive but critical approach. The standard model above, including an inflationary ECOP, is the best we have, but with many problems. We can cautiously adopt this standard model, provided we do so in a critical way, using all available observations to delimit its nature and carrying out all possible consistency tests, acknowledging the observational limits and the resulting uncertainty and looking for all viable alternatives. So this is to say, look, we don't know what inflation is, we don't know what the cosmological constant is, we don't know what the dark matter is. Nevertheless, this is the best theory we've got, and it may be that all these problems will go away as we keep looking at it. Well, I'll say just a little bit more about this. Firstly, we need to use real observations. And part of the problem is each set of observations you get brings in a series of auxiliary functions and parameters. When you look at each kind of source, you get absorption, source evolution, luminosity functions, you get bias, you get tilt, you get detection and selection functions related to the astrophysics of the problem. And the cosmological problem is each set of sources brings in these auxiliary functions. You can't fit the data without these auxiliary functions, but their existence then loosens the link between the theory and the observations. Because you can fit almost any observations by varying all of these auxiliary functions, which themselves depend on the astrophysics of the problem. An example is the homogeneity of the universe and radio source counts. I've already said the universe is incompatible with all observations if there is no evolution of radio source counts. We have no proper theory of evolution of radio sources. And so that's where the auxiliary function, namely the evolution of radio sources, intervenes between the observations and the interpretation and prevents you from using the radio source counts to determine anything about cosmology. Now, most of the universe is empty, with matter concentrated in isolated clumps separated by vast regions of empty space. And the homogeneity of the Friedmann-Lemaitre models is only a realistic representation when we're averaging on large averaging scales. There's a really interesting theoretical problem here for relativists. Light rays travel in empty space because light rays travel between galaxies, not through galaxies. Otherwise, the light wouldn't arrive here. And Weyl focusing takes place. It is the Weyl tensor which focuses the light which travels between galaxies, rather than the uniform matter which is Ricci focusing, as in the Robertson-Walker models. The theory we use, which I put on the board earlier today for some of you, is based on a completely homogeneous model, and it assumes that the matter is traveling through the intergalactic medium regarded as a smoothed-out medium. That is exactly the opposite of the reality of observations. In reality, the light goes between the galaxies where the space is empty, and the Einstein equations are the vacuum field equations, actually, where the light is actually traveling, which is the opposite of the models we use in order to get the theoretical equations. And it's a really intriguing question as to why the actual observations in the real lumpy universe should approximate the observations that you predict from the Robertson-Walker description, which is completely smooth. And there are kinds of ways of dealing with this, like using things called Diorader distances, but this is a really interesting part of real analysis. I won't go through the details of that. Unless we live in a small universe where we're able to see many times around the universe, there are essential limits to what we can observe because of the limits of particle horizons, the limit of causal contact, and visual horizons, the limit of visual contact. So we have no direct knowledge of what lies beyond the particle horizon. No electromagnetic observation of what's beyond the visual horizon. So, for instance, the predictions of chaotic inflation, the idea that there are all these other domains out there, are simply unverifiable. There is no way we can get any observations of those regions. We need to relate to real physics, relating dynamics and observations to real physics as opposed to potential physics. For example, just because you write down a Lagrangian or potential for a scalar field and then derive the consequences does not necessarily mean one is relating to real physics. But that seems to be the attitude. Write down a Lagrangian and it's real physics. This depends on whether such Lagrangian or potentials mirror the behavior of matter or fields that actually exist at some time in the real universe. And whether that is so or not is determined by experiment. And in fact, there's an interesting thing about that. For the Einstein equations, it's been known for a long time you can solve them from right to left, which is the standard way. Matter implies geometry. But you can equally solve them from left to right, which is geometry implies matter. What you can do, actually, you can choose any geometry you like and put it in on the left-hand side and solve these equations algebraically for the stress tensor on the right. And you get an exact solution of the Einstein field equations by determining the hypothesized matter required to give the desired geometrical behavior. Choose any behavior you like for the universe, run the field equations this way, you get a prescription for matter, you say that's the way matter is, and you've solved the field equations exactly. That's called the Singh trick. For instance, in the Robertson-Walker models, there are only two independent dynamic parameters because of symmetry, the energy density and the pressure. From any dynamics, whatever, write the Friedmann equation in this form. You can choose the scale factor as desired. These equations give the pressure as a function of the density needed to obtain an exact solution with that evolution. So if you assume that equation of state, you can get whatever evolution you want. And you can represent it as a scalar field and determine the needed potential, requiring the kinetic energy to be positive. So the point about it is, you've got to tie the matter down to real physics, not to potential physics. Important parts of what is done in present-day theoretical cosmology are essentially the Singh trick carried out in the context of Robertson-Walker geometries. I'm running out of time, so I'm just going to say, I would like to refer you to what I will call the physics horizon. We cannot experimentally test the physics that is the relevant physics at very early time with the relevant energies way beyond what can be achieved in accelerators on Earth. We face the existence of a physics horizon which is just as important for our testing of cosmological theories as the particle horizon and the visual horizon. This is the energy range separating those physical properties and theories which can be tested by experiments in the solar system from those that cannot. This applies both to gravitation theory and to particle physics. And then we haven't determined the hypothetical fields supposed to be responsible for inflation. The hopeful link with particle physics is hypothetical rather than actual. We can't test the Wheeler-DeWitt equation for quantum cosmology. Nobody's got a way of testing if that equation is actually correct. We have no good tests of quantum gravity theories, whether string theories or loop gravity. And in fact, we don't even have good experimental evidence on the classical gravitational theory applicable at the time of nuclear synthesis. We don't know if general relativity is true on those scales and at those times. Or to quantum field theory then. The assumption is quantum field theory applies in those extreme circumstances, and we know exactly how quantum field theory is in those conditions. There's a huge extrapolation taking place. Extrapolation is the name of the game, and it could be wrong. And finally, we certainly can have no test for theories of initial conditions of the universe. Some of my colleagues are producing theories of initial conditions of the universe. Now, you can do that as a mathematical game. You run full tilt into the fundamental feature of the uniqueness of the universe. It's not possible to test any such theory, even in principle, because there's only one universe, and we can't rerun it with the same or altered conditions. There's only one universe we can observe, I should say, and we can't rerun it with the same or altered conditions. Insofar as physics involves determining the effects of tried and tested laws on the nature of physical reality, we are outside its domain when we talk about theories of initial conditions for the universe. Because of these considerations, any fundamental approach to cosmology must necessarily face up to philosophical issues that give the essential framework of understanding. The major issues are the uniqueness of the universe combined with observational and testing uncertainties. And what is important here is what we regard as the scope of cosmology. What is regarded as a satisfactory cosmological theory depends on what issues of explanation and cause we choose to address by that theory. And a really important issue, when you're doing cosmology, you need to decide, do your cosmology going to look at existence of life and questions of meaning, or are you happy to talk only about physical issues? Is your cosmology going to try to talk about questions of ultimate causation or only to physical effects with the nature of the laws of physics taken for granted? You need to make decisions on these issues. Depending on the answer given to those questions, the resulting theory will be more or less dependent on the underlying philosophical stance adopted. The deeper we probe, the more philosophy will be important. Choice of your answer, what you think cosmology is a philosophical choice. It's perfectly okay to choose not to look at ultimate issues, treating cosmology purely as a technical issue, and that you can do, and that is a major philosophical choice. Because of the existence of visual and causal horizons and the physics horizon also, there are many limits on what can be observational proven. And so one of the philosophical issues is which has priority in your theory, physical explanation or observation and testability? Which you choose changes how you approach cosmology, and most of the inflationary theorists place physical theory above observation. They think which was also Dirac's viewpoint, if you remember the famous statements by Dirac. For example, in the chaotic inflation proposal, theory takes precedence over geometrical and physical testability. And you get very, very confident statements from some of those theorists. This is the way the universe is, even though there not only has not been any test, but there never ever will be any test of what they are saying. And the particular key point where the tension between theory and testability present needs discussion is the issue of the multiverse, as I've already mentioned. This is being increasingly defended because it is the only purely scientific approach to solving the puzzles raised by the anthropic issue, as I mentioned, why the universe has the peculiar properties that allow intelligent life to exist. For example, Steven Weinberg uses it to explain the value of the cosmological constant. But is this physics or metaphysics? A point I've already made. The major problem is any such proposal can have no link to any direct observational test. Even showing that other universes in the postulated multiverse physically exist, let alone determining their properties, will forever be hypothetical. Consequently, you can explain anything you want by postulating the existence of an ensemble with suitable properties. You choose what you want to prove it, I'll find you a multiverse that will prove it. Which means this concept has no solid predictive power, because any concept that explains everything actually explains nothing. So the conclusion, given the problems outlined, the essential need is to be critical but not overcritical, to adopt the middle road in the context of an integrative explanatory framework. A larger interpretive scheme taking seriously the uniqueness of the universe and the limits on observations. What we're looking for is overall explanatory power and coherence compatible with observations. A hot Big Bang following inflation is the best theory we have, but we must recognize its problems, look for alternatives, and perform all possible observational consistency checks.
Just a comment. Just like this morning, I warmly applaud you for using your position to tell it like it is, for your rather negative characterization of cosmology today. I mean, to me, it's really the biggest generator of garbage in physics, and it just is unbelievable. And the quality of the people working in this field is just steadily declining. I mean, some of them. You mentioned, for example, one of your things was positive kinetic energy. There are people around who wants to give up that as well. So I think it's really important at this school for the young people to hear this from somebody like you, that that one has to have standards in physics.
Thank you very much. Thank you.
I also appreciate your critical analysis of the situation. What is the way forward? If you look at the cosmic microwave background, the new measurements of that, we can measure tensor things. There's a lot of information there that presumably we will get, which will give us clues on the way forward. Is that the best chance, or what are the next measurements that will help us?
The joker in the pack is the gravitational wave experiments. Now, we don't know how successful they're going to be. We don't know how sensitive they're going to be. But those let us see, in principle, way, way beyond the visual horizon. If inflation is true, we're seeing much, 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 much further with those gravitational wave experiments than with a microwave background. So if you're going to put in long-term money into cosmology after the microwave background, gravitational wave detectors is the place to go. Of course, the dark matter experiments are also important. If we could find dark matter in a laboratory, then, wow, we would just have a huge, huge sort of tie-up. I mean, one of the really great disappointments in early inflation, in the first models of inflation, the hope was that the scalar field would be the Higgs. Wow, things would have tied up in such an incredible way. You see, that would have been fantastic, but that didn't work. The neutrinos is the next one. Neutrino telescopes. But that's not going to. That doesn't have quite the same potential because it doesn't go nearly as far. But still, it goes a lot further than the surface of light scattering. So neutrino telescopes, whatever one can do, one can try and do. So those are the two things: neutrino telescopes and gravitational wave telescopes. And then, of course, theory.
I want to take a slightly different view of things here to the one you put forward, George. I mean, agreeing with a lot of what you said. I think that there are 2 points that need to be made. One is that, and you made this point yourself, that there is actually no current alternative to the inflationary paradigm that is successful at explaining features of the universe with all its gaps, which I fully agree with. And that is a very powerful reality because people have tried extremely hard to come up with alternatives. Even some of the most exotic alternatives, like the ecborotic universe, are claimed by certain inflationary theorists to simply be inflation in another guise.
Yes, correct.
In some sense, they're right.
That's right.
And that is a very, very sort of imposing reality that we just can't get around. The second point I want to make is that I don't see doom and gloom in all these crises. Cosmological constants is the wrong size.
It means there's work for all these graduate students.
For the young people here, they should take a positive spin on that as well. So what we're really running into, I think, is grappling with what quantum gravity theory is. This is a big problem that's been around for decades.
Well, that's one of the issues, but then one of the things, what we need to do, the trouble with a lot of what we're getting at the moment, we're just getting this overall package. And it's not explained clearly that the microwave background peaks actually are not due to inflation at all. What they're due to is the oscillations of the universe way, way after inflation, in fact, at very recent times. And where inflation comes in is simply in setting homogeneous initial conditions way, way back. But actually the peaks are in a certain sense not due to inflation, they're due to physics much, much later than inflation. And what we need to do is to not just have these big packages, but to have it separated out into the different components of the package. Yeah. Yeah.
It's not quite true.
Yeah. But for instance, Bob Walt has a kind of alternative to inflation. One of the really interesting issues is the question, to what degree can you get those kind of correlations out of EPR type of effects in a universe which does not inflate? Now that's an interesting kind of question. Bob Walt's view is that you do indeed get such correlations of a certain time, but it's a question if there's big enough and on right enough scales. Now there's a quite interesting kind of problem for people to look at.
I want to allow the students to ask questions, but if nobody's asking a question, maybe I can ask you 2 historical questions.
Yeah.
They're just for my own personal curiosity. The first question regards Milton Humason, and I have no vested interest in him. He's not related to me in any way. I was always wondering why Hubble got all the credit and Humason got nothing. Why Humason did most of the work. Is it because Hubble came from a very wealthy family and Humason came from a very, very poor family in France?
I'm afraid I can't really answer that, but I would come with a slightly different line. It was Slipher who first got the first magnitude redshift curve, and he's kind of pushed aside. Now, it's true he didn't have the statistics, but he had the first. In fact, in Eddington's book on the universe, he quotes the data from Slipher. He doesn't quote Hubble.
So how did the relations between Emerson and Hubble eventually play out?
Yeah, I'm sorry, I can't. I think one might remember that Hubble was, if I've got it right, a heavyweight boxer, so it wasn't a good idea.
My second historical question that I'm always curious about is that I know that Friedman and then Lemaitre came up with Big Bang standard cosmology that we know and love. So how did Robertson Walker come in?
Well, Friedman came up first with the K as +1. 2 years later, which came from
Friedman only had K for +1?
1922.
Okay.
1924, he had K as -1. He never got K as 0, which is kind of curious. Lemaitre came in 1927. Friedman treated it as a mathematical problem, and from the current, in hindsight, he never calculated the redshift. Okay, whereas Lemaitre calculated the redshift. That makes a huge gulf between Friedman and Lemaitre. And then Lemaitre went on to talk about the primeval atom and all sorts of stuff which Friedman didn't see. But of course, Friedman died, so he didn't have the chance to do it.
Lemaitre was also constrained by the fact that he was a priest, a Catholic priest. He had to deal with the Pope and so on.
Now, what Robertson and Walker came in was, there's an intermediate figure. Milne came in with his kinematic theory, in which he didn't adopt the Einstein field equations. And you got then the distinction, which is still a very useful distinction, to first do kinematics, which is when you do everything you can do on the basis of geometry without assuming any specific field equations. And then you throw in the dynamics. And what basically Milne started it off, but what Robertson and Walker did was to set on a sound foundation the analysis of Robertson-Walker models without any dynamical field equations. And so, and that is relevant to today, because today we're altering the field equations at all sorts of will. And so, in a certain sense, what Friedman did and Lemaitre did is not nearly as relevant as what Robertson and Walker did, because what they did was to establish the geometry, the dynamics, and the symmetry properties and so on of the field equations without assuming any field these universes without assuming any field equations. And so that provides the basis for using all sorts of altered dynamics that you want to do. Robertson and Walker remains valid, Friedman and Lemaitre don't.
But Friedman and Lemaitre, in order to do what they did, they must have been, they must have been able to write down the metric, which is what the textbook called it.
They did.
Robertson, Walker, and Lemaitre,
yes.
Right?
But the first person who wrote down the metric, including all three forms, was Robertson in 1929.
I see. Friedman only had K +1 and -1.
Yes. And for instance, it is Robertson was the first person who drew that beautiful embedding diagram of the De Sitter universes in his 1933 review article. And Walker produced the fundamental theorem. The fundamental theorem is isotropy everywhere implies spatial homogeneity. That was proved by Walker, not by anybody else. That theorem has been improved since then by Ellis, Guerin, and Sachs, reducing it to the microwave background radiation. But in a sense, the reason for believing the Robertson-Walker models is that the Walker theorem, isotropy everywhere, implies spatial homogeneity.
Any more questions? Yeah. Do you have any vaguely plausible ideas as to what the dark matter is, or is it?
No. The particle physicists have many hypotheses, massive neutrinos, gluons, all sorts of stuff. I have no idea. And of course, what you must remember, it is always possible. We deduce the dark matter on the basis of our gravitational theory. It's always possible, and there's some people who are trying it. Maybe the problem is in the gravitational theory on those scales, and there isn't any dark matter. We're using the wrong theory of gravity. And given the importance of dark matter, unpopular as that is, that's the kind of thing people must keep on testing.
And just a sort of related question. Dark matter is one thing, and dark energy is something else.
Yeah.
And as soon as we discover that the universe is accelerating, we say that, we'll introduce another scale of field and see if we can solve that problem.
Yeah.
So people talk about quintessence. And quintessence fraction is a really
ad hoc ideas to solve this problem, which we're not even sure is a problem now that we have verification from supernova to set the supernova data. Yet, it strikes me as if one takes chaotic inflation seriously, or the idea of multiverses seriously, has anyone asked what happens if these things, can they actually intersect with our universe? Can you get an inflating patch now? In let's say chaotic inflation, can you get an inflating patch now intersecting with?
Well, to me, one of the things which is completely missing in inflation is a proper analysis in chaotic inflation of the junctions between the inflating and the other areas. I think you know that. I think it's one of the things which is completely missing. What you might expect, you've got an inflating era there and a hot Big Bang era there and some kind of intervening domain. You might expect this would give off gravitational waves, all sorts of stuff. And to me, that's one of the big things which just hasn't been looked at properly.
Okay, so, no further questions?